Hello everyone. In this episode, I would like to introduce quasi-periodic waveform generative model, which is a pitch adaptive CNN-based speech generative model. This is my outline. First, I would like to discuss about the problem of unified vocoder. Then I will introduce our proposed QP structure with PDCNN and show how we apply this module to both autoregressive and non-autoregressive speech generative models. In the end, I will compare our proposed methods with existing methods to explore the philosophy of the proposed designs. In the last episode, we summarized the vocoder technique into two categories. The first one is source filter vocoder. A source filter vocoder includes an excitation generation module and a resonance filtering module. The input are acoustic feature and the output is speech waveform. The second one is unified vocoder, which directly models speech waveform with a single neural network. The input can be acoustic or linguistic feature, and the output is also speech waveform. However, there are some weaknesses of the current unified vocoders. So I would like to introduce our proposed QPNet and QPPWG in this episode. As we know, speech is a quasi-periodic signal, which include periodic and aperiodic component. The periodic component has a long-term correlation, and the aperiodic component has a short-term correlation. As a result, modeling speech using a fixed unified network without any prior knowledge of audio periodicity is inefficient. For example, as shown in this figure, the fixed receptive length and the sampling sparsity make the network oversample the periodic signal, which means the receptive field includes many redundant samples. Furthermore, because of the unified model nature without prior knowledge of pitch, the unified vocoders do not explicitly model periodic components. Therefore, it is difficult for this vocoder to generate speech with an accurate pitch when condition on acoustic feature with F0 is not in the observed F0 range of training data, or on thin spectra and F0 pairs. Here are some examples. First, I played a sound with normal F0. The first one is nature sound.
The hills ran up clear above the vegetation in spires of naked rock.
The second one is PWG generated speech.
The hills ran up clear above the vegetation in spires of naked rock.
The third one is QPPWG generated speech.
The hills ran up clear above the vegetation in spires of naked rock.
We can find that both PWG generated and QPPWG generated utterance are very similar to the nature sound. Now I play the sound with double F0. The first one is what we expected.
The hills ran up clear above the vegetation in spires of naked rock.
We can find that the pitch is become much higher. And then I play the PWG generated speech.
The hills ran up clear above the vegetation in spires of naked rock.
We can find that the speech quality is significantly degrade, and the pitch is much lower than what we expected. And I play the QPPWG generated speech.
The hills ran up clear above the vegetation in spires of naked rock.
We can find that although the speech quality is still degrade, it's much better than PWG generated speech. And most important is the pitch is more consistent with what we expected. Now I would like to introduce the proposed module of QPNet and QPPWG. The first one is PDCNN. We know that the main drawback of CNN and DCNN is the fixed geometric structure. Specifically, convolution with a size 2 kernel can be formulated like this formula. Y is feature map. I denote input, and O denote output. WC and WP are changeable weight metrics for current and past sample respectively. T is the time index, and D is the direction size. For CNN, D is set to 1. For DCNN, D is predefined and time invariant. However, for our proposed PDCNN, the direction size D prime is pitch dependent and time variant. That is, the original direction size D is multiplied by a time variant pitch dependent scale E to get the direction size deform of PDCNN. For the implementation of PDCNN, since directly modify the CNN module to dynamically change the direction size is difficult and not hardware friendly, we dynamically index the input feature map, which is equivalent to change the direction size. Specifically, the result of a 2x1 CNN are equivalent to the summation of the result of two 1x1 CNN, namely the CNN-C for the current sample and the CNN-P for the past sample. Therefore, we first get the direction size of each sample. And then we index the input feature map of the 1x1 CNN-P according to the direction size. Finally, we summation the result of CNN-C and the CNN-P to get the PDCNN result. With the pitch-dependent direction size, each sample has a specific effective receptive length corresponding to its pitch. For example, as shown in this figure, although signal A and B have different frequencies, by changing the sparsity of the CNN sampling grid, their effect receptive field still contain the same number of cycles. Since speech has periodic and aperiodic component, we propose a QP structure to simultaneously model them. The QP structure is composed of cascaded fixed and adaptive blocks. The fixed block with DCNN and adopt DCNN to model the short-term correlation of a periodic component. The adaptive block adopt PDCNNs to model the long-term correlation of periodic component. And its network architecture is dynamically changed according to the instantaneously FDU. First, we apply the QP structure to the WaveNet vocoder. The main difference from WaveNet is that QPNet replaces several fixed blocks of WaveNet with the proposed adaptive blocks to improve its pitch contributivity and modeling efficiency. With the proposed QP structure, QPNet achieves similar speech quality and higher pitch accuracy than WaveNet, while the model size is half of that of WaveNet. However, although the model size is reduced by 50%, it is still large. The large network and autoregressive mechanism make the generation still far away from real time. As a result, we apply the QP structure to parallel waveform PWG, which is a compact and non-AR generative model. Since the discriminator and the multi-STFT loss show the effectiveness in PWG chaining, the proposed QPPWG inherent them. And the main improvement is apply the QP structure to the generator. Even if the model size of PWG is only 3% of WaveNet, QPPWG still will reduce 30% model size of PWG while achieving similar speech quality, but higher pitch contributivity. On the other hand, compared with QPNet, the main difference of QPPWG is the non-AR mechanism, Gaussian noise input, low waveform output, and only 5% model size. According to our objective and subjective evaluation in our paper, the QP structure shows the effectiveness in both WaveNet and PWG-like models. The QP structure makes these models have better pitch contributivity with a small model size while keeping similar speech quality. If you are interested in the experiment result, please check our papers. Since PWG and QPPWG direct output low waveform samples, we can easily dissect the model to understand the internal generation mechanism. According to the visualized cumulative intermediate output, we can find that the PWG gradually generates both harmonic and non-harmonic component. However, the QPPWG model with an adaptive to fixed order first generate the harmonic component and then the non-harmonic component. Light is the first 10 adaptive blocks focus on modeling pitch-related components, and the last 10 fixed blocks focus on modeling spectral-related components. In contrast to the QPPWG model with an adaptive to fixed order, the QPPWG model with a reverse order, fixed to adaptive order, first focus on non-harmonic component and then generate harmonic component. The visualized result confirm our assumption that the adaptive blocks modeling the pitch-related component with long-term dependencies, and the fixed block modeling the spectral-related component with short-term dependencies. Although QPPWG is a unified vocoder, its cascadic network structure is very similar to the source filter model. The adaptive block analogous to the excitation generation, and the fixed block are analogous to the spectral filtering. Compared with the neural source filter model, which also adopt a non-AR DCNN architecture, the main difference is the excitation generation of QPPWG is performed by a neural network. The idea of a dynamic update attention mechanism, making a network know where to look at each time step, is not new. Deformable CNN is an example, which achieves marked improvement in the object detection task. Specifically, for CNN, the sampling grid is fixed, so the coverage of a single kernel is also limited. The straightforward way to enlarge the coverage while keeping the computation cost the same is by extending the direction size like a DCNN. However, the fixed offset of the sampling grid are inefficient. The enlarged coverage may also contain many undesired areas. Therefore, the authors of deformable CNN proposed learnable time-variant sampling offset to make the network focus on the desired areas. The idea is very similar to our proposed PDCNN for changing the index of the input feature map. The main difference is that the deformable CNN adopt a neural network to predict the index, but the index of PDCNN is parametric determined by the input pitch and the sampling rate. Therefore, we can say that PDCNN is a special case of deformable CNN with prior knowledge of pitch. For our proposed modules and models, PDCNN is very simple and can be easily integrated into any CNN-based module. The QP structure makes a pitch-dependent adaptive network available, and its source filter-like architecture is more tractable and explainable. Compared with original WaveNet and PWG, the proposed QPNet and QPPWG respectively achieve better pitch contribution and similar speech quality with smaller models. If you would like to listen to more demo samples, please check our demo page. If you want to try QPNet or QPPWG by yourself, you can also find the GitHub link on the demo pages. We implement the QPNet and QPPWG by PyTorch. This episode is finished. Thanks for your attention.